Hi, Daniel. Are you here?
I'm here, yes.
Perfect. Can you share your slides?
Of course.
Perfect. If you make it full screen. Yeah. Okay, great. Okay, we still have like 2 more minutes, but okay. So you have 15 minutes. I'll give you a warning after 12. And then there will be 3 minutes of questions after your talk.
Gotcha.
Let's wait for another minute. Okay, I think it's time to start. So welcome back everyone to the second session of the working group 2. This session is mostly devoted to beyond diagonal studies. And the first speaker is Daniel Adamiak from Ohio State University, and he will talk about the small X Helicity phenomenology. You can go ahead, Daniel.
Thank you. Thank you for the opportunity to let me talk. I'll be discussing our attempts to understand the helicity of quarks inside of the proton at small x, talking about work that I've done in collaboration with Yuri Kovchikov, Wally Melnichuk, Dan Petoniak, Nobuo Sato, and Matt Sivers. Okay, so we all know by now that the proton has the same quantum numbers as a bound state of 3 quarks, but when we look at it at higher resolutions and higher energies, we see that it's a whole collection and distribution of quarks and gluons. And we would like to understand exactly how these quarks and gluons are distributed. In particular, we can look at the angular momentum of the proton. So we know that the proton has spin 1/2, and this must be comprised of, at the very least, the contribution from the spin of the quarks and the gluons, as well as the orbital angular momentum of the quark and the gluons, because when you probe at higher resolutions, these particles aren't just all point-like, they're free to move around each other. In particular, we would like to look at the total spin from the quarks. In existing experiments today, they can only measure a finite portion of the total quark spin contribution, and they find it only accounts for 30% of the total proton spin. Now, that's an important note that we can only measure a finite portion of SQ. That means in order to get to the rest of SQ, we need to calculate it somehow. And I'm here to claim that we can calculate most of SQ. How do we do this? Well, SQ can be written in terms of this integral of the helicity parton distribution functions. So delta Q and delta Q bar are the helicity parton distribution functions for the quarks and antiquarks respectively. Delta Q just measures the net helicity of the quarks. These are functions of resolution and Bjorken X. And of particular note here is that in order to get the total spin contribution of the quarks, we need to integrate these helicity PDFs all the way down to Bjorken X equals 0. Because Bjorken X is inversely proportional to the center of mass energy of our DIS experiment, that means if we want to measure these experimentally, we'd have to measure them up to an infinite energy, which is sort of outside of our budget. So how do we deal with this? Well, we need a theory to describe these helicity distribution functions that we can trust to extend down to all the way to x equals 0. So what is that theory? Well, it turns out that these Helicity PDFs can be described in terms of something called the polarized dipole amplitude. What is that? Well, it's simply the object where you have a quark-antiquark dipole pair that pierces a proton medium, where one of the quarks exchanges helicity information, denoted by this gray box. This polarized dipole amplitude simply needs to be integrated up to get the Helicity PDFs. And this polarized dipole amplitude is merely a function of the rapidity separation between the dipole and the particle that emitted them, as well as the transverse distance between the quark and antiquark. Okay, so we've written down what this polarized dipole amplitude looks like. Can we calculate it? Not directly, but we can differentiate it with respect to Bjork and X to see how it changes as we change X. And through that, we can then construct an evolution equation for G. So this was done by Karchikov, Adamiak, and Sivers with their KPS evolution, where we have this derivative with respect to rapidity y, which is equivalent to a derivative in Bjork and X. And we see that it results in a whole bunch of gluon exchange diagrams that we need to resum. Of particular note is that the thing that we resum here are double logs in 1 over x, contrast with the unpolarized case where you resum single logs in 1 over x. A consequence of this is that small x isn't quite as small as we're used to, and we can actually describe a larger region of data when we talk about polarized DIS as opposed to unpolarized DIS. Okay, can we resum these diagrams? What does it result in? As usual, it results in an infinite hierarchy of integral differential equations that we can simplify if we make some appropriate assumptions. So for example, or in particular, when we consider the large NC limit, so large number of colors, that resummation of diagrams simplifies to the following statement. Okay, where G naught here, this first term, is a flavor-dependent initial condition that needs to be fit to data. Remember, this evolution equation just describes the evolution. It doesn't tell us how we start. And this initial condition is a simple Born ansatz, where it's just 3 undetermined coefficients multiplying the arguments that G depends on. So we've got A, B, and C that need to be fit for each flavor of Q, so up, down, and strange. Moreover, we have this auxiliary function gamma, which obeys its own separate integral equation, but importantly, it just mixes with G. So there's no third object that it mixes. So actually what we have here are 2 coupled integral equations that are closed. That means we can compute this numerically and go all the way back up to calculate our spin. So mid-talk recap, we are interested in calculating the total contribution to the spin of the proton from the spin of the quarks. It turns out that this is an integral of the Helicity PDFs. The Helicity PDFs themselves are an integral of this polarized dipole amplitude. And this polarized dipole amplitude is an integral of the polarized dipole amplitude. So we've reached the bottom rung of the ladder. We're done. All we need to do is integrate up and we get SQ. Okay, well, not quite. We still need to determine what this G naught is, this initial condition. How do we constrain that? Well, we need to look at different observables. And what enters observables are linear combinations of these Helicity PDFs. So to shorten things, I'll write that delta Q plus is the sum of the quark and antiquark Helicity PDFs. So there are 3 relevant HPDFs, the one for the up quark, down quark, and strange quark. Heavier quarks are suppressed. Okay, so what are 3 observables? So we need at least 3 observables to constrain these guys that have linearly independent combinations of these HPDFs. Luckily, we have 3 such observables, at least in DIS. We've got the G1 structure functions for the proton, the neutron, and for parity violating DIS with gamma Z. Unfortunately, we only have data for G1 proton and G1 neutron. So G1 proton is this particular linear combination of the Helicity PDFs, and G1 neutron is obtained by taking the isospin symmetric version where we swap the up and the down contributions. And unfortunately, we don't have any data for parity violating DIS. So currently, we can't obtain these Helicity PDFs just from DIS, but we will continue our analysis purely in terms of DIS for simplicity's sake. trying to obtain other observables is later work, which I'll talk about later. Okay, so what are the measurements that we need to make? Well, we can measure the G1 for the proton and neutron from double spin asymmetries. This is just a measurement of the cross sections for when you have the electron and the proton both have positive helicity or when one of them has negative helicity. Okay, so we have data for that. Can we fit it? Does our theory, describe the existing data? Well, here we go. Here's the world's first fit of this small x theory to polarized data with a cut of x less than 0.1. And so the black dots and bars are the data and their uncertainties for various experiments. The red lines are our theory fit to proton data. Blue lines are our theory fit to deuteron data. Green lines are our theory fit to helium data. So it's looking pretty good. I should make note that we have a cut of 0.1 because this is small x theory. We are unable and we don't expect to be able to describe all data, in particular large data. But is 0.1 really that small? Well, remember, we are resumming double logs in 1 over x. So in the case for unpolarized DIS, we find that we need x of about 0.01, which translates to an x of 0.1 in polarized DIS. And I should further say that this is a good fit. The chi-squared number of points is about 1.01. Or rather, I can say that the existing data is insufficient to falsify our theory. So it seems like we're on solid ground so far. I'd be remiss not to mention that this is a JAM small x talk. So we're only able to do these fits with the help of the JAM framework, where it involves a Monte Carlo generation of parameters that helps tend towards chi-squared minimum or a minimum chi-squared. And I should also apologize to my JAM collaborators for single-handedly using up all of the computing hours allotted to the theory section. Sorry about that. I'll try not to do it again next time. Okay, so now that we fit the existing data, can we make some sort of predictions? Because remember, the whole point is to motivate that, we're trying to motivate that our theory can be used to extend down to x equals 0. So here's a plot of a prediction for G1. The red bands are our prediction using our theory. So something I haven't mentioned yet, that should be pretty well understood, but I'll say it again for completeness sake, is that G1, it's a function of x and q squared, and you have a choice for which variable you want to predict and which variable you want to parameterize. So these blue DSSV curves, for instance, they use dglap to predict the q squared dependence, but then they're forced to parameterize the x dependence. A consequence of this is that even though your q squared fit is very good, and in fact your x fit is also very good, once you go beyond the region where you have data, the uncertainty for your x fit blows up. So here for their dark blue curve, they incorporate EIC pseudo data, but that data only goes to about 10 to the minus 4, and then the uncertainty blows up after that. The advantage to using theory to describe x and then parameterizing q squared is that when you go down to small x, your uncertainty remains constrained. So just look at the inset plots where we have our uncertainty over our prediction. For existing data, we see that this ratio remains fixed, even as we extend down to x very small. And once we incorporate EIC pseudo data, we see that that uncertainty shrinks massively and remains flat even while other parameterizations blow up. So this seems like a strong argument for, yes, it seems like we do have good control over the statistical uncertainty as we extend down to small x. Maybe we can trust this theory to integrate up and calculate the total contribution to the spin of the proton. I should also say that a unique prediction here is that we do predict large negative G1 for the proton. Okay, so here's a preliminary extraction of the Helicity PDFs. The reason it's preliminary, as I said, we're only looking at G1 proton and G1 neutron. We need at least one more constraint to nail down the different PDFs. So as a simplifying assumption, we've set delta S plus to 0. So this isn't a real extraction, but it merely demonstrates that we do have the machinery to extract the Helicity PDFs. And once we're able to extract the Helicity PDFs, we can extract delta sigma, which measures the spin contribution from the quarks as a function of x and q squared. And again, we get good control as x goes down to very small values. Okay, so to summarize, we have a theory that describes the Helicity PDFs in terms of the polarized dipole amplitude. We performed the first small x fit to all polarized data, and we managed to then take that fit to constrain the initial condition and predicted G1 all the way down to x equals 10 to the minus 5, most importantly, while maintaining control over the uncertainty. And finally, we demonstrated a preliminary extraction of the Helicity PDFs and the quark spin contribution. So then in the future, what we'd like to do and are currently doing is to look at other observables to finally nail down the one last constraint to separate the different Helicity PDFs. And once we do that, we can then make a more solid claim about how the different Helicity PDFs look like and how they recombine into the total contribution to this from the spin of the quarks. On the theory side, what remains to be done is this was in the sense, the most leading order calculation. One would also like to include large C and an F, which includes quark emission and absorption into the evolution. And this was done by Yuri Kovchikov and Josh Tauber. And in addition to that, we'd also like to include high order corrections. So we were resumming double logs. We would like to include single log contributions, and of the same order would be to include running coupling. So again, see Josh's talk. He's talking tomorrow at 1:45, ironically in the spin session, not the small x session. So remember to swap over at the appropriate time. And that is all I wanted to say. Thank you very much.
Daniel, thank you very much for this very nice talk. And also thank you very much for being on time. We have time for questions, and I see that Yacine already has a question. Yacine, please go ahead.
Yes, yeah, thanks for this nice talk. So I have a question about the precision of the calculation. So you already mentioned it towards the end. Mm-hmm. So you basically, when in the Bjorken limit, you can gauge your certainty at the given order in perturbation theory by varying the factorization scale. In here, since you are doing a double logarithmic calculation, right, which is in general not very accurate, right? You would like to calculate, as you mentioned here, you want to go to single logs and include running coupling to. So how do you really control your precision here? And if you don't have, I mean, in principle, I expect to vary X here to be able to gauge your uncertainty. And did you do that, or what's the result if you did?
What do you mean by vary X to gauge the uncertainty?
Well,
we predict.
You have an insert because you are doing this. This is a small x resummation, right? Mm-hmm. So you have logs of 1/x. So when you vary X, you might generate single logs, right?
Yes.
So this is double logarithmic, so higher, so basically varying X falls into, higher orders, right? So by varying X, you might gauge the terms that you are, subleading logarithmic contributions that you might neglect.
Right, so I guess to put it simply, what we've demonstrated here is that the statistical uncertainty remains small, but we haven't demonstrated what is the size of the single logarithm contribution. And there is some evidence that it could be quite large, but I think the takeaway that when we included that the statistical uncertainty will still remain small. But yes, we do think it's important to calculate the single logarithmic contribution and include it, and potentially it will change these curves quite a bit, but that we're currently doing that. And we feel it's best to just calculate them directly as opposed to making an estimate right now for how much of an effect they have. Does that answer your question?
Yes, but I think, this somehow gives motivation to compute really, going to higher orders and really control better the accuracy of the uncertainties. Yeah, theoretical uncertainties, so to speak. Thank you.
We have another question from Renaud. Renaud, please go ahead.
Thank you. So my question is kind of a follow-up question to that, because as we know, for most physical observables, x and Bjorken x are proportional to each other, which is the reason why if Bjorken x is small, then x is small. But the thing is, so if you know the x dependence of the distribution, you will know the Bjorken x dependence of the observable. But I'm not sure the opposite is true. And what you're doing is you're working at x equals 0, and then you have the evolution equation, which gives you dependence on usually a scale which is chosen to be Bjorken x rather than Feynman x. And in the spin sum rule, x is the variable you want to resum. So is there some kind of uncertainty that due to the fact that you don't have x, you have Bjorken x in your evolution equation there?
That's a very good question that I'm not sure how to answer right now. I'd have to think about it.
Okay, thank you.
Well, okay, thank you very much, Daniel, for the nice talk again. So let's move to the next speaker, Gabriel Santiago. So Gabriel, can you share your slides?
All right.
Can you screen?
Can you see my slides and my mouse?
Yeah, perfect. You can start. I will warn you after 12 minutes. You have 15 minutes overall. Thanks.
All right, thank you. All right, thank you all for coming to my talk. I'm Gabe Santiago, and I'm going to talk to you about work I did with Yuri Kovtchikov on the small x asymptotics of the Quark-Sivers function and how it relates to the spin-dependent Odderon. Okay, so what is the Quark-Sivers function? It's one of the 8 leading twist TMDs for quarks inside of a hadron, and those give you the transverse momentum structure of the quarks. So they can give you the correlations between the transverse momentum of the quarks and the various possible polarizations of the parent hadron, or equivalently, the correlations between the polarizations of the quarks and the polarizations of the hadrons. Now we know how to do the evolution with the hard scale Q squared for these. It's the Collins-Soper-Sturman evolution equations. But the small x evolution equations for the TMDs is still being worked out, and we want to move that project forward by finding the small x evolution equation for the Sivers function. Okay, so the Sivers function in particular, it's the TMD that gives you sort of the density of unpolarized quarks inside of a transversely polarized proton. And that manifests sort of as an intrinsic asymmetry in the transverse momentum of the quarks inside the proton. So if you generate single spin asymmetries, you have some transversely polarized proton moving along, and there's a left to right asymmetry in the motion of the quarks. And so that produces a left to right asymmetry in the production cross section. And that comes in as a spin orbit coupling term, where you take the cross product of the proton's transverse spin with its longitudinal momentum and dot that into the transverse momentum of the quarks. So this TMD, it comes in to define it with the unpolarized quark density F1Q. So you get this linear combination of the unpolarized quark density with the Sivers function, F1T perp. And that's just the usual non-local operator product, where you have the 2 quark fields and a staple gauge link connecting them, and you project out with the gamma plus matrix. Now we're looking for the small x asymptotics, and the small x asymptotics for actually the gluon Sivers function are known, and that's going to give us an important hint for what to do for the quark Sivers function. So back in 2016, Boer and others showed that all of the T-odd gluon TMDs are generated by the same gauge link, which couples the QCD Odderon to the spin of the proton. So they have this nice formula where you relate all of the gluon Sivers function, gluon Molars function to this spin-dependent Odderon operator. Now, what is the Odderon? It's just this 3 gluon C-odd exchange in QCD, and it's been historically very difficult to detect. But also in 2016, Giovanni and Zhao showed that the spin-dependent Odderon can contribute to cross-sections and then asymmetries if you assume that there's an asymmetry in the transverse momentum wave function of the proton. So that's hinting again that it's going to be connected to the Quark-Sivers function, since that would be the same structure that the Sivers function generates. And very recently, we had a very exciting announcement by the D0 and Totem collaborations that they detected an Odderon in proton-proton and proton-antiproton collisions. And that's actually the sort of original asymmetry that the Odderon was proposed to explain. So we want to see if we can find this Odderon as a contribution for the Quark-Sivers function. Now we want to find this all at small x, so we need a framework for determining the small x asymptotics of TMDs in general. And in 2019, Kovchikov and Sivers constructed this high energy scattering approximation operator formalism, and they explicitly found the small x asymptotics for the Helicity TMDs and the Quark transversity TMD. So the main strategy here is you rewrite this non-local operator product in terms of Wilson line correlators in the form of dipoles, and then you'll find evolution equations for those dipoles. So the dipole operators, it's this trace of Wilson lines where you have fundamental and an anti-fundamental Wilson line for a quark-anti-quark dipole, and that resums all these eikonal exchanges with the target. So if you go ahead and rewrite the quark correlator matrix that contains the Sivers function in this way, you end up having to introduce a new kind of Wilson line into your correlator. And this is actually going to be a polarized Wilson line that communicates with the transverse spin information of the proton. So what is that new operator? Well, you can think of it as the same dipole that we had before, and we're going to work in sort of a shockwave approximation of the target interaction, where this blue rectangle is the shockwave. And we add a sub-eikonal insertion here that is an interaction communicating the spin information about the proton with the quark that's traveling along this Wilson line. And so that gives you this polarized Wilson line operator. And if you want to construct the Helicity TMDs, what you do is you put in a sub-eikonal insertion here. And if you want to do transversity TMDs, you get a sub-eikonal insertion. And so once you have these new Wilson lines, you can put them into a polarized dipole and evolve those dipoles to get the small x evolution of the TMDs. Okay, so we're looking at the Sivers function. We need the transverse spin information about the proton. So I said that comes in at a sub-eikonal order. So you have these two possible insertions that you can put into that little box. You have an operator where your quark propagates along an ordinary Wilson line, just doing eikonal exchanges. And then it has a sub-eikonal exchange where it interacts with the gluon field of the proton. And so you get this local operator inserted between two Wilson lines, and you integrate over all possible insertions along the x minus path of the quark. And then you also have an operator where you do a quark exchange. So you have your regular Wilson line propagation, a sub-eikonal quark exchange, and then propagation of the gluon through the background proton field. And that's an adjoint Wilson line. And then another sub-eikonal quark exchange, and finally regular eikonal Wilson line resummation. So that gives you actually a bilocal operator that's inserted between these Wilson lines, and you integrate over all the possible insertions for each of these quark exchanges. So if you go ahead and sum up all those diagrams, you can put together this nice operator, which gives you the polarized Wilson line, which would go into any of the transverse spin-dependent TMDs. So you can use this in principle to construct not only the Sivers function, but also the transversity, Pretzlosity, and Worm-Gear functions. So this operator sort of looks like you have some quark where it's starting off with transverse polarization chi in the S underline direction, and it goes through, it has this sub-eikonal exchange with the proton, comes out with a chi prime. And so, physically, the Sivers function is the coupling of the proton's transverse spin to the unpolarized quark density. So we're going to look for a term that's something like delta chi prime. So we have all these various chi prime structures here. And if you just look at the first one, there's something that looks like similar to just the Wilson line here. And that's actually going to end up being the main contribution. So if you go ahead and do all the algebra and you drop the light quark masses to make things simple, you get the only contribution that actually goes into the Sivers function term is this single imaginary part of a correlator. And these Wilson lines are your ordinary eikonal Wilson lines. So this contribution is actually going to come in just with a power of 1 over x. It's going to grow at small x. And this correlator actually looks very familiar, something we saw before, which was the Odderon. In the dipole model, the Odderon is just summing over the possible exchanges of 3 gluons in this color symmetric configuration between a dipole and the target. And so you can write it exactly as this imaginary part of the correlator that we found inside the Sivers function. So plugging that back in, we get a small x Sivers function that comes to its power of 1 over x and is exactly the spin-dependent Odderon that Boer and others found for the T-odd gluon TMDs. And this is going to generate exactly that asymmetry in the transverse momentum of the protons quarks. So we want to look and see what happens if we do a model calculation of this. So we calculate the Odderon in the diquark model, where we have a point-like proton that can split into a point-like quark and a point-like scalar particle called the diquark, which has no spin, but all the other quantum numbers of an antiquark. And so you calculate the Odderon by just taking the possible 3 gluon exchanges and sandwiching them in between the wave functions for the proton to split into the quark-diquark pair. And you get this classic logarithm cubed term for the Odderon exchange amplitude, and you can put that in. And this gives you an estimate for what the Sivers function at small x is going to look like. And exactly like I said, it comes in as power of 1 over x. So this is an eikonal term. It's not going to be suppressed as you go to smaller and smaller x. And it has interesting behavior because it has 2 powers of the proton mass and 2 powers in the denominator of some infrared cutoff. And the infrared cutoff, just by dimensions, has to be a mass scale. So you end up getting this behavior where if I take lambda QCD to 0, all of the other mass scales in QCD have to vanish. So the Sivers function just cancels out all the mass terms, and you have a non-zero Sivers function even at 0 proton mass, which seems to be just an interesting feature of this model calculation. I'm not sure if that would generalize, but the big important takeaway is that we have a non-zero spin-dependent Odderon contribution at the eikonal level for the quark Sivers function. Now, that's very good news that it's eikonal, so it's going to grow at small x, whereas the leading order calculation, the traditional calculation of the Sivers function, gives you a power of x. It's sub-eikonal. So as you look at smaller and smaller x's, you'll have a harder time detecting it. But we have this eikonal Sivers function, and we expect it to be exactly a power of 1 over x, because if you look at the evolution for the Odderon, it's known to have an intercept of exactly 0 at leading order and next to leading order in QCD, in the planar limit of large N C QCD, and even in n equals 4 supersymmetric AMLs. So we have a lot of evidence that this thing isn't going to receive any suppression even as you go to very, very small x. And so that really opens up the possibility of getting further experimental detections of the Odderon, in particular the spin-dependent Odderon, by looking at spin asymmetries such as the transverse single spin asymmetry and semi-inclusive DIS when we're working with future colliders such as the EIC. All right, thank you. Are there any questions?
Thank you very much, Gabriel. This was a very interesting talk. We actually have time for questions or discussions, so if you have any, please go ahead. Bohan, please go ahead.
Hi, can you hear me?
Yes.
Yeah, nice talk, very interesting. So what can you say? So your conclusion is that the Quark Sivers function is going to be sizable at small x, right? What can you say about Gluon? I mean, the Sivers Gluon. Can you do similar conclusion? Can you have similar conclusion?
So that's actually the work that Boer and others did. They got that the gluon Sivers function comes from the same spin-dependent Odderon. So it would be, it have this similar 1 over x behavior, which seems to be pretty well protected even under small x evolution. So it should be growing with small x, but you know, experimentally, the Odderon seems to be a very small effect for some possibly non-perturbative reason. So if the Odderon isn't non-perturbatively small, then yes, both the quark and the gluon Sivers functions should be somewhat sizable and grow as you go to small x.
Very nice, thank you. Good.
Thank you.
Any other questions? Oh, okay. If not, thank you very much, Gabriel. We can move to the next talk. So our next speaker will be Guillaume Beuf, and he will talk about next-to-eikonal quark propagator. Guillaume, can you share your slides?
Okay, here. Okay, is it okay? Can you hear me?
Yeah, so it's all good. Okay, so you have 15 minutes. After 12 minutes, I will warn you, so you can start.
Okay, so I will talk about so next-to-eikonal quark propagator in the CGC and applications. So this is a work that I did with Tolga and Alina and Arantxa. So we had a paper out in December already. So the idea, I mean, like the general idea is that we want to go beyond the eikonal approximation that is usually used in QCD studies at low X, so for example in CGC or BFKL, and consider power surplus corrections and energy limits. So as a first building block, we consider the quark propagator, and so then we calculate the quark propagator through a shockwave at next-to-eikonal accuracy. And then as a simple application of this propagator, we consider quark nucleus scattering at next-to-eikonal accuracy. So, okay, so let's consider high energy scattering of dilute projectile on the dense target. So typically a proton or virtual photon on a dense nucleus. That would be described in the CGC, for example. But here, for simplicity, we replace the dilute projectile by a quark or anti-quark parton as a projectile, and then the nucleus will be just modeled by a Gluon background field. So here, like the eikonal approximation is actually correspond in that setup to a shockwave approximation for the background field. So if the target of the background field is taken to be going in the X magnus direction, shockwave approximation amounts to first have the infinite Lorentz construction of the background field to just to have support only at X plus equals 0, so a target of 0 widths. Moreover, we can drop the X minus dependence of the background field due to Lorentz time dilation, since then X minus would play the role of time for the target. And in addition, we also have a large hierarchy between different components of the background field, which is given here. So if we have a large boost factor, so we consider boosting the background field, so by a large boost factor of gamma. So then the A minus component would be enhanced. The perp component will be, unchanged by the boost factor, and the A plus component would be power suppressed in that case. So okay, so in general, in usual low X QCD or CGC, we consider, for example, a background field of with this type of behavior due to all this thing, and so then the eikonal approximation here amounts to just taking the leading power in the high energy limit to take the leading power in the total energy of the collision, or equivalently in the boost factor. So that is what is done in most of the CGC studies, and we want to consider subleading power with respect to this eikonal approximation. So mainly because they can be potentially large corrections to CGC predictions at moderate energies. So for example, at EIC or RIC especially. So here, since we want to go beyond the eikonal approximation, we need to include some effects beyond that. So first, we need to to consider effects related to the finite width of the target. And actually the main effect would be that now we have to consider transverse motion of the projectile parton while it is crossing the target, which is not exactly a shockwave anymore. And in addition, we need also to include the effect of the A-perp component of the background field now. And so this would be the two effects which would be relevant at the first subleading power, so at next-to-eikonal accuracy. And in general, we could go beyond and write down a full power series in terms of some small parameter like this, which would be related to the, so with L plus being the width of the target and K plus the large momentum of the projectile parton, and Q square will be any transverse scale of the target in the problem that we consider to be fixed in this limit. Okay. So now let's go to the quark propagator. So in general, we write the quark propagator in background field as a sum of free contribution, which is just the usual free quark propagator, and plus a correction due to the interaction with the background field. So at eikonal accuracy, there is just a contribution which contain only a minus the A minus component of the target, like the enhanced component, whereas at next-to-eikonal accuracy, where there is also corrections due to A-perp insertions. So okay, first at eikonal accuracy, now since the A minus component is enhanced, we need to resum it to all orders, and that is okay, well known. But okay, like here we can write down the combine the free propagator and this A minus resummation. So and write down the first two contributions to the propagator with depending on the relative sign of depending on the ordering of x plus and y plus. So in that case here we have a quark propagating from y plus to x plus, and in that case we have effectively anti-quark propagating from x plus to y plus. So here we get resummation of A minus into a Wilson line like this in the fundamental representation, whereas in the case of anti-quark propagator, propagation, that would be anti-fundamental. And in addition to these two terms, we have a leftover term which is actually instantaneous in time, yes. Okay, which is already present in the free case. Okay, so now going to next-to-eikonal correction. So first, let's consider the contribution with still only the A minus component. So now I will, starting from now, I'll write only the case of quark propagator, like literally crossing the target. So from before the target to after the target. And so now when we write down the diagrams and calculate, we find out we can write this thing as, okay, like the eikonal term, which has the Wilson line, and then two next-to-eikonal correction associated with the transverse motion of the quark inside the target. So one here is a drift term, where you see the incoming and outgoing momenta of the quark. Yeah, and here that would be a term which would be associated to Brownian motion within the target. Then there is also next term would be a contribution with one insertion of A-perp. So here the full contribution to the propagator would be, first we start with a eikonal quark propagator, then we have this A-perp insertion, and then we continue with, again, the eikonal quark propagator. So that would give a next-to-eikonal correction. And okay, we can just insert the previous expression for the eikonal propagator and calculate, and we find such kind of things, where here we have, again, Wilson lines and some insertion of something which contain both A-perp field component and also some transverse derivative. and then Wilson line for the eikonal propagation after this insertion. And then the thing is that we can consider also two insertion of the A-perp. So again, eikonal propagator, insertion, eikonal propagator, insertion, eikonal propagator. And naively, that would be, that looks like a next-to-eikonal because we have two insertions. But actually here we can remember that in the eikonal propagator, there was instantaneous piece. And due to that piece, that would give a non-zero contribution here already at next-to-eikonal accuracy. And since it's instantaneous, then the two transverse field would be end up at the same point basically. So we have a insertion of like double insertion like this. So okay, so now we have the three contributions. But the thing is that here we have this particular spinor structure, which was different from the one that was present in the term with only A minus. So we have to just rewrite this. So we can rewrite that as a unpolarized piece and as a Helicity dependent piece. Remembering that this commutator gamma I gamma j is proportional to the Helicity operator, basically for spinors. And so then we can write the sum of the three terms as one unpolarized contribution, which starts already at which contains the eikonal plus some next-to-eikonal correction, and then some Helicity dependent contribution, which starts only at next-to-eikonal accuracy. Yeah. So okay, so here.
4 minutes.
Sorry.
We have 3 minutes left.
Okay, so. So then this unpolarized part is very analog to the result we had in the case of only A minus insertion, except that now the transverse derivative are promoted to covariant derivative by including the A-perp contributions. So that's a nice cross-check to see that we get something gauge invariant here. And whereas Helicity dependent piece now. It comes with this decorated Wilson line with insertion of Fij component of the background field, which which correspond to longitudinal chromomagnetic field. So okay, so we have this propagator now at next-to-eikonal accuracy. So we want to see the content of that. So let's consider the simplest observable, which would be Quark target scattering. So we can write such kind of LSZ reduction formula for this Quark target scattering, which would relate the S matrix for that process to the propagator we just calculated, and then okay, from that we can get scattering amplitude. So then. Okay, again, scattering amplitude is just as I wrote before with the eikonal contribution, then the Helicity dependent part with Fij, and then the Brownian correction and the drift correction here. Now we can write down the differential cross section for quark nucleus scattering like this. And okay, we obtain the result in such a way where here we had at the eikonal accuracy we have just a fundamental dipole operator as usual, and here I split it into a real part and which contains the Pomeron and imaginary part which is the Odderon here, and then if for that observable the Helicity dependent piece drops, and we have this decorated dipole operator associated with drift, and this one to Brownian motion, so they come in this thing. And to understand a bit what's going on, it's we can also redo the same calculation, but for anti-quark scattering on the nucleus, and we get exactly the same result except for a minus sign here. And so that tells us that actually this next-to-eikonal corrections are odd odd under charge conjugation in the same way as the Odderon, where the Pomeron is even. And then here we see that also only the imaginary parts of this contributes. So basically all these corrections associated with transverse motion inside the target here are odd under both signature and charge conjugation, like the Odderon, whereas the Pomeron is even under both things. So then instead we could also consider the helicity asymmetry by taking the difference of the two helicity of the two possible helicity of the quark instead of the sum. And so then in that case we would get contribution only from this Fij type operator, so this decorated dipole operator here. And actually in the case of anti-quark, we would get exactly the same result. So actually this this term here now is odd under signature transformation, but even under charge conjugation. So it has a behavior which is neither like Pomeron or Odderon. And moreover, actually this thing, if you try to evaluate it into an unpolarized target, you see that it would vanish. So actually that would require, for example, longitudinally polarized target, and that would be then the result that you would get typically for double longitudinal spin asymmetry. Okay, so as a summary, so we have calculated full next-to-eikonal correction to the quark propagator through the background field, including both correction due to transverse motion, so drift and Brownian motion of the parton while crossing the target, and correction due to the A-perf component of the background field. Then there would be still a plus component of the background field and the X minus dependence of the background field, which are not there, but because they would appear only at next-to-eikonal accuracy. We obtained a gauge invariant expression, so that's a nice cross-check. Yes, so only we have helicity dependence starting only at next-to-eikonal accuracy, and that term is actually consistent with the result of the Royo state group that we have heard already in the previous talks. Then in general, like the complete calculation could be compared in principle with the result of Giovanni, and that is under progress because it's done in a pretty different way. So apparently it's most of it is an agreement. There is maybe a doubt on one term that Giovanni has and that we don't, and we still are working to understand what's going on. Okay, so we applied also to a very simple observable here. I mean, simple observables like with unpolarized and helicity asymmetry cross sections for quark nucleus scattering. But then, of course, this can be. That the quark propagator is a building block which can be used for many more complicated observables, and that we'll do that in the future. And so, for example, we are considering to calculate the AIS digest production in that setup at next-to-eikonal accuracy. Okay, thank you.
Thank you, Guillaume. So we already have two questions. Yacine, you were the first, so you can go ahead with your question.
Yes, hi Guillaume. Yeah, I have a question concerning, so you introduced L plus for your calculation, which is, I guess, some longitudinal cutoff, right, to confine the field within a certain interval. So my question is, so this is this was not required at leading eikonal, right, in the eikonal approximation. So now you introduced it to compute higher or high power in the non-eikonal powers. So is this necessary, or
so
should we then go back to the
in a way? So okay, first, I mean, physically we expect the field strength to be vanishing outside of the target, right? So to have only we are expecting to have only a finite extent along X plus for the support of the of the field strength, so the F mu nu. And basically that like the L plus would be like the extent of that support of the field strength. But then, okay, and in principle, we could do most of our calculation with just that assumption. So basically assuming that there is only a finite support along X plus for the field strength, and then we boost, so that makes it smaller. And that's it. Then the thing is that for the part of the calculation which is outside of the target, in principle, we could have a non-zero A mu, which would be now a pure gauge field. But it's just a bit annoying for the power counting. So we basically assume that we are in a gauge where we can take this pure gauge field to be zero, basically, both before and after. But in principle, yes, it's not really. It's more for convenience, yeah.
Okay, I see. Because my question is related. Usually in the shock wave, you send the extent of the shock wave to infinity for the fields, but for the impact factor, you treat the shock wave as being a pancake, right? So it's
you integrate, like you forget about the integration range. So yeah, you continue the integration range outside, and usually that was because of that. So like I think, I mean, like the way I understand it is that traditionally we were thinking in terms of light cone gauge, and in that case the field was like the field A mu was literally zero outside of the shock. So then we could extend the integration range for the Wilson line to plus and minus infinity because it's zero outside. So that was kind of trivial. But then, okay, if you want to consider beyond light cone gauge, you have to think a bit more about what's going on with the pure gauge field outside and how you extend the integration outside, and then you need to include like transverse gauge link at infinity or not at infinity. Actually, I mean, you have to think about what you are doing. Yes.
Okay, we can discuss it offline. Yeah, thanks.
Okay, we have another question from Yoshitaka.
Yes. Hi, Guillaume. Can you show me the next leading order operators, the next-to-eikonal operators?
So that was so for the propagator or for the
so this one. So you have an unpolarized and the polar helicity dependent part. So the unpolarized part, it doesn't explicitly proportional to, it's not explicitly proportional to the helicity, but if you take the matrix element of this operator in the polarized proton state, then don't you get a spin dependence?
You mean, wait, I didn't hear the unpolarized or the polarized?
Yes, unpolarized. It doesn't contain helicity.
Okay, here I was talking about unpolarized from the projectile point of view, like for the quark I send, basically. So this is unpolarized, and this is, I mean, this is independent of the helicity of the quark I send, and this is just the helicity of the quark I send. But then I have not thought too hard about what happened on the proton or the target side, just that this guy here needs some polarization to be non-zero. Here I have not really thought too much what's going on here.
Okay, yeah, because I discussed the matrix element of this operator.
Yeah. Okay.
So I can send you some.
Okay.
We have another question from Renaud, but okay, Renaud, if it is not urgent, I would suggest we discuss it offline with Guillaume.
It's not urgent, but it's 1 second actually. So is there a reason why you don't take L plus to 0 now that you have that second term in the expansion? Because if you were consistent, you would take A plus equals 0, right, in that second term? Or is it an additional factorization scale?
Oh. What, L plus?
Yeah.
I mean, yeah, okay, like this thing is proportional to L plus, basically.
Yeah.
So my small parameter is L plus over K plus times some.
Yeah. So why didn't you go on with the expansion here?
I mean, okay, so then the thing is that, Okay, so this is like because of the integration range is proportional to L plus, but then
Yep.
I mean no, it's
Oh, okay. Well, if the question,
okay,
if the answer is long, we can discuss offline.
Yeah.
That's
Okay.
yeah. Thank you.
Okay. Yeah.
Okay, thank you guys. We're really running late, so thanks Guillaume for the talk. So we continue with our next speaker, Jamal Jalilian-Marian. So Jamal, could you please share your slides?
Yes, so let's see. Okay, I think I'm sharing my slides. Is that right?
Yeah, you're sharing it. If you can make it full screen, it would be.
Now it should be okay. All right. So thanks, Tolga.
No, not really. You're still not full screen.
Oh, on my laptop shows full screen. And I don't know what else to do. Let's see.
Okay, anyhow, okay, it's big enough so you can continue.
All right.
We can still read your slides. It's okay.
Hold on, sorry. So let me. Oops, now I don't know how to share. Oh, sorry, hold on a second. All right, let me share the screen, and you guys, if some aspect of it is not visible, just
okay.
Ask me. Sorry, I say now it should be full screen, but anyways, okay.
Okay, go ahead.
All right, thanks, Olga. So this is part of a very long-term project with very slow progress. Typically 2 steps forward, 1 step backward, and hundreds of steps sideways. So let me tell you what's the latest. The eventual goal is to have a formalism which has saturation and color glass condensate as a limit, as a small x limit, but also has the standard collinearly factorized PQCD and the Glap evolution at what I call large x. So that's the eventual goal, and here is some work towards it. A quick reminder of the saturation that at very small x, if the number of gluons is very large, one has to include multiple scattering, and the way we do that is via iconal multiple scattering. Generically, that leads to PT broadening, and then you also go to smaller x, and then you have to worry about the x dependence, and you do that by evolution equations, Jungwalk and BK. And the signatures are that in case of, for example, inclusive spectra, there is a suppression of RPA. And in terms of the azimuthal angular correlations, there's the wayside peak disappearance and so on. But again, let's remember that when Larry and Raju formulated this, they told us there's a semi-hard scale that emergence is the saturation scale, and that has to be large, much larger than.
Sorry, Jamal, but I cannot see the slides changing. Do you change the slides, or are you on a first?
Oh no, oops, I changed the slide. Can you see it now?
Yes, thank you.
Oh, that means I cannot go full screen. Okay, so let's see if I can make this bigger. Thanks, Anna. Is this screen bigger now?
It's fine.
Okay, I'll stick with that. I have no idea how that works, but okay. So saturation scale has to be larger, and the reminder that it is really 1 GeV squared for a proton at very small x of several times 10 to minus 4. Nevertheless, this is probably the closest to a first principle QCD approach to multi-particle production possible. It can do many things, and it leads to many important results and predictions. But keep in mind that this is at best good for x's of 10 to the minus 2 or smaller. One can motivate that x for a nuclei in terms of coherence length. You want the full longitudinal size of the nucleus. In case of a proton, it's really from Hera phenomenology. One maybe can also motivate it from saying that at x is that small, the logs become large enough that have to be resummed. All right, so the basis for all this is the iconal scattering. In case of quark scattering, you basically because the small x target field is independent of the x minus coordinate, as was referred to, then one can treat this as scattering from this particular kind of a color background field and resum it. It is important to realize this is the infinite energy approximation. The projectile quark does not lose any of its energy. All the exchange momenta are transverse, and as a result, the projectile quark basically gets deflected by a very small amount, small angle deflection, and the PTs of order of QS or so. And formally, actually, the quark stays on the light cone. And these multiple scatterings are summed into efficiently into a Wilson lines, and the correlators of these Wilson lines are what appear in DIS observables, as well as this hybrid formulation of proton-nucleus collisions. And the X dependence comes from the Jumwak and BK. And now beyond that leading order type argument, there has been significant progress in various aspects. Some of you already have given talks. And I'll mention just two particular avenues. One avenue is the next to leading order corrections, significant progress. And the other one is what we just heard about, sub-eikonal corrections, but these are all at very small x. And since I want to motivate large x, let me, I hope you can see this figure from EIC, because on my screen it looks a bit funny. So this figure, if you can see, it's the dihadron correlations at EIC at the highest energy of 90 GeV. And it shows you the kind of x's that the target gluons contribute. And you see that for this moderately kind of PT, the target x gluons are not at small x. They're actually at pretty large x. X is mostly larger than 10 to the minus 2. And of course, EIC has that good feature that in DIS, one can fix x and look at fixed x. So that's one caveat to have in mind. EIC will have a large amount of phase space, and would be really nice to understand the transition from large X PQCD to small x saturation. And also remind you what we know, or most of what we know about saturation of nuclei comes from comes from Rick and LHC now. And there's a very simple question that one can raise, and that's what is the kinematics contributing to observables at Rick? For example, this is the single inclusive pion production in proton-proton collisions, and remind you that there is nothing nuclear there. Left-hand side figure is from using perturbative QCD collinear factorization. Right side figure is from CGC. And you see there's a huge discrepancy in the kind of X's involved that dominate the cross-section. And the reason for that discrepancy is because at small x, we're making a very, very drastic approximation. We're really taking the minimum value of x that goes into a collinear factorization and saying that one particular x dominates the whole cross-section. So one should be very careful using what we have learned from Rick and mid-rapidity LHC towards EIC. So with that long introduction, I want to say what the goal is. This is really the goal, to have this unified formalism. If one can do it, rewards would be tremendous. Basically merging jet physics with saturation and all sorts of correlations. Now, of course, this is a tall order. How would you go about this? The idea is simple, right or wrong, we'll see, but the idea is basically based on how you would do this at small x. You can basically formulate the problem as a scattering problem. Again, consider scattering of a parton from the target. In case of small x, you have the eikonal approximation, as we've seen and love, and that's basically scattering from small x gluons of the target. Now, that does not cause any deflection. You get all these Wilson lines. The question is, what happens if I include large x scattering, or scattering from the large x degrees of freedom of the target? There, of course, I have both quarks and gluons as a first approximation, or first, the simplest thing to do. Let's worry about the large X gluons. Large X gluons of the target can carry large longitudinal momenta. As a result, they can basically transfer that large longitudinal momenta to the projectile. and cause a large deflection of the projectile. So now you don't have this propagation in the original direction anymore. There's a large angle. So then, of course, you still want to include multiple soft scattering. So the approximation involved is we would like to include all soft gluon or all scattering from these small x gluons of the target. Those are those thick lines, the Wilson lines. And we would like to include one exchange with the large x gluons of the target. That's the wavy line inside the circle, like these guys. So those are the large x gluons exchanged with the target. Now the complication is now you have to include diagonal lines everywhere before and after the large exchange, large x gluon exchange. And also now the large x gluon itself will interact with the small x gluon. So rather than one iconal diagram, now you have multiple. So this can be done and you get the amplitude. It's easier to evaluate these things using spinor helicity formalism. And if you do that, you see that right away inclusion of these large x gluons leads to some interesting effects. And let's always keep in mind in the context of RIC and LHC, large x gluon means you're going to large PT. So the PT involved is large. So first of all, you see that you get this double spinosymmetry, ALL. Now, again, this is at higher PT. This is not at small x. This is at larger x. And if you want to do this, you can do this at small x using saturation. That's where those subiconal terms come in. But that's at small x. And reminder that all the, or pretty much spin observables, these spinosymmetries are sitting at fairly intermediate PTs, which are larger x's. The second thing that is not present in the standard saturation is this, what I call baryon transport or beam rapidity loss. Remember, in case of hybrid formulation of the scattering, the projectile quark does not lose any energy. It keeps it all. Here now it can get some energy and lose some of it to the target or vice versa. So it loses rapidity. And this is something we already know from RIC that there's beam rapidity loss, couple of units or so. So those are the kind of things you get right away. Now that was what I described as a leading order type calculation. The most interesting thing is, of course, to do a loop correction and then see whether you really get the GLAP at large Q squared and whether you get the small x Jumwalk or BK at small x. So that includes radiation of a gluon. Now you have to allow that from every leg that I showed in those diagrams, and that's quite complicated. A somewhat simpler problem is to consider photon radiation, because photons don't interact with the target. Now that itself is also interesting on its own, because then you can use that to investigate photon jet or photon hadron correlations, azimuthal correlations from low PT to high PT. And also now you can, for the first time, investigate forward-backward rapidity correlations. That's something that you cannot do using standard saturation. So what are the diagrams involved? You basically have to go back to the diagrams I showed and allow a photon radiation from every quark line you see. So broadly, one can classify these diagrams into 4 classes. Radiation of a photon either before or after the exchange, large X gluon exchange with the target, and with or without the large X gluons interacting with the small X gluons of the target. Again, these are long expressions, not very illuminating to show, but again, if you can go, you can use the spinor helicity formalism. So I'll show some of the, for example, for this diagram, the first diagram, then it's very straightforward to evaluate these. And right away, you see that you also get the spinosymmetries, the double spinosymmetries in this case. Now, I don't really know experimentally whether this can be measured here or not, but it's interesting that every time you include the large X exchange, you're going to get that double spinosymmetry. All right,
Jamal,
so
3 more minutes, okay?
Oh, I'm pretty much done. So what does it have to do? This was what I described was kind of an attempt to do hybrid formulation of PA and extend that to large X. What does it have to do with DIS? So we all remember at small x, or actually in general, not just small x, you have the crossing symmetry of the amplitudes. And at small x, when we did the in this hybrid formulation, when you do proton nucleus going to, let's say, hadron and photon production, the diagrams there are related to the DIS diagrams by a very simple crossing of the photon and the quark line. And then you can show that the two diagrams in the PA case can be written as three diagrams in DIS, which actually really add up to one diagram. The last diagram, if you can see it, that's where the quark and anti-quark interact. So that's a very nice feature. So what I just described, all you have to do is allow the photon to be virtual, which is quite simple. You just allow to have one more polarization degree of freedom. And then use, you can either calculate it brute force or just use the crossing symmetry. And from here, what I described, we can actually get the digits in DIS. And now the difference between what we already know at small x is now this will be good at not just small x, but that we know we also have it at large x. It will be extremely interesting to see how the transition from the GLAP region and large x physics happens to small x physics. So I won't bother reading the summary, but I'll just highlight the part that I want to emphasize. And that's really that we should all remember that the large part of the kinematic phase space at all the available collider facilities and the proposed electron-ion collider is really at large x. And since we're mostly interested in small x, there's quite a bit of uncertainty on the kinematics that we're exploring in these RIC and LHC type processes, and whether that can be directly translated into DIS, where you can really fix x. Whereas in RIC and LHC, there's a interplay between PT of the produced guy and the x's that you probe. So I think it's essential that we investigate, understand this transition from large x to small x. This is a very tall order, but if successful, then I think one can really extend the CGC and saturation processes to high PT and large x, and then investigate everything that we have done, but in this combined kinematics. And of course, there's a lot to be understood that I basically swept under the rug, like issues of gauge invariance, issues of what do I really mean by large x versus small x, how do you even like define initial condition. But again, as I mentioned, DIC is in 10 years or so from now, so there's plenty of time. And of course, the more people jump on it, the better. So thank you very much, and I'll stop here.
Jamal, thank you very much for the nice talk. We already have questions. The first question is from Farid. Farid, you can unmute yourself and ask your question.
Hi, Jamal. Very interesting progress. I have a question related to the how does one determine the x of these large x gluons that you include in your computation? Can those be determined from kinematics? Like in standard small x, as you mentioned, one takes the minimum x, but what are the x's involved in these large x parton corrections?
Mm-hmm. So very nice. So that's one of the things that I swept under the rug, and unfortunately I don't have a nice and short answer. So the way I've been looking at this is how to distinguish in a sense between large x and small x, and not to double count, because these you know, when you have the small x, you have these color charges rho and there's sources and so on. So there are a couple of, to answer that question, one has to finish this, what I call radiation of a gluon, which will give me the loop corrections.
I see.
Then I will know what are the pieces that are giving me DGLAP, what are the pieces giving me Jumwalk, and how to put them together. So there are a couple of things one can do, right or wrong at this point, I don't know, but one would be a brute force approach. Remember that cutoff that we always have in mind, x of 10 to the minus 2. One thing to do is to say, okay, whatever is at 10 to the minus 2 or smaller is my small x CGC. Whatever is larger than 10 to the minus 2 is these new diagrams that I included. That's a brute force of doing it. Another way of doing it would be to say, remember at small x, we always argued that the field strength, the A mu is high. It's 1 over G. And at large X, it is basically order G. So one way to do that would be kind of like playing with the strength of the coupling G and decide at some point, okay, how large or small is G? And that would be my small x saturation physics, and the other one would be large X. But again, to emphasize, I do not really have a good answer for that. So we'll see.
Just another quick comment. So there is some recent developments by Adrian and Risto in which they compute gluons at moderate X from Lycon wave functions. Maybe one could couple your computation with theirs in some way. Just a comment. Thank you.
Would be very, very interesting. I have to say, I haven't read the paper carefully, and that issue is going to be there in a sense. So as a reminder, when we do collinear stuff, what do? We have the distribution functions, and we parameterize them at some initial Q naught and then evolve with Q squared. At small x, we start with some initial X naught and then evolve with X. Now, if I want to have this general formalism, what do I start with? With what X, what Q? So one has to sort that out, and I think it'll become more clear after this gluon radiation. Part of it will be what to put as initial condition and what to put as part of the evolution. So for example, when you start with 3 valence quarks and now allow them to radiate a gluon, and then do you call that part of your initial condition as part of your large X rows, or do you count that as part of the evolution of the 3-parton system? So there are a lot of things I still don't know, and especially that paper, I have to read it more carefully, but it's very interesting.
Very interesting. Thanks, Jamal.
Jamal, we have another question from Yacine.
Yes, just a quick question. So you started out with this hybrid formalism, which is more like 2-to-1 process, right? The quark nucleus to a quark, right? But to connect to large X, what you want is 2-to-2 processes, right? You have 2-parton scattering, and then you have a point-like interaction. That's the infinite, the Bjorken limit. So did you investigate this in your formalism to see how the 2-to-2 process would show up in your kind of hybrid kinematics?
Good. So what one needs to do is, if you take and this you can also do at the small x, and I think people have done it. I think Al and Rolf Bayer did this, but you can take the high PT limit of the cross section, and then what you're going to get is, in the small x case, what you get is the target is now, you basically recover the gluon distribution function, but only in a sense, the first rung of the ladder, but before any evolution. In this case, you will also get the same thing, I think, but the first rung, and then when you put in the evolution, then it will be the gluon distribution function, but evolving with dglap, not with not the small x evolution. I think that's what you're going to get. And the hard scattering part, d sigma dt, you recover that anyways. The only difference there will be that when you recover d sigma dt in the eikonal limit, that is really the small x limit of d sigma dt. So that t is really the small x limit of the general t. In our case, I think you'll get the full t. Do you know what I mean? The SUT?
Yes. Thanks. Yeah.
I think that's going to happen, but again, I don't have the final result yet.
Jamal, our last question is from Ian Balitsky.
Oh, hi. Sorry, I don't see anything except my screen.
Sorry, I was trying to unmute myself. Question is the following. You are probably talking about rapidity evolution, yes, of the target. And DIS is evolution with respect to normalization point. How you will reconcile them?
Well, I think I mentioned earlier, so the way to reconcile them, if possible, first of all, I don't really know the answer, but if it is possible, it is going to come from when I start my leading order diagrams and I do a gluon radiation. If I do that, it is going to contain, in principle, both the renormalization of my large X gluon, that is going to be my DGLAP evolution. This is the way I'm thinking. I don't know if it's right or wrong, but this is the way I'm thinking. One gluon radiation, remember now my large X gluons will radiate, unlike these small X gluons. So that is going to give me my DGLAP evolution, or what you call the renormalization, standard renormalization of the operator. And the other parts that I do, the small X fields are also going to be subject to evolution. That will be the standard part, the standard X evolution of the saturation picture, the Jim Walk and BK. I think that's what's going to happen, but again, we'll have to do it and see whether that's the case.
Actually, we have done with Andrei Tarasov this exercise. We obtained the DGLAP from rapid evolution, but only in the first loop. So I think at some point you or somebody else need to get to loop result from DGLAP from rapid evolution. It will be more technically involved, but it will show you the way for how to deal with this transition from small x to DGLAP.
So that's the part, actually, I've seen your paper and I should refer to it, but the part I don't understand, that's why I didn't mention it, is I do not, as far as I know, and please correct me if I'm wrong, you cannot do structure functions from your approach, F2 and FL.
I think I can definitely do it, but the price to pay will be that will be two evolutions in DGLAP. First is evolution with respect to rapidity, and second, more trivial in a way, renormalization of the theory. So DGLAP evolution will be more complicated in this approach, but I think it's doable. Again, I didn't do it,
right,
but
okay.
That's my feeling.
Right,
okay,
so that's what I meant. So in the paper you had, that has not been done for structure functions. That's right.
Agreed.
Okay. But okay. You're probably right that it will not be a standard evolution in the sense of one, very likely it will have parts, one part evolving as Jim Walk, one part evolving as DGLAP. And the question is the interaction, the mixing part. I don't know, we'll see.
Well, thank you very much, Jamal. We need to do the next talk. Our next speaker is Giovanni Chirilli. Giovanni, could you please share your slides?
Yes.
Perfect. Great. So now we can see.
Is it full screen?
Yeah, it is full screen. We can see it, no problem. You have 15 minutes. I will give you a heads up after 12.
Okay, thank you. All right. I will talk about the behavior of quasi-PDF at small x. And I will start with the definition, which is the original definition of the quasi-PDF, and then I will consider the actual. Yeah.
Giovanni, hold on a second. Your slides are not clear. It's hazy.
Huh?
You cannot really read them.
Hazy.
Well, they looked good to me.
It was good to you? Okay, maybe it was only me. I'm sorry. Okay, I will give you another minute. You can continue.
Okay. Okay, let me. So I need to go to full screen again, right? Is it looking good or?
Now it looks good. Yes.
Okay.
So now there's no problem.
Okay. So then I will talk about light rate operator with point splitting, and this light rate operator with point splitting will be exactly the quasi-PDF. And the technique to consider the behavior of this object at high energy is the energy operator product function. Therefore, I will briefly review. Then I will just present the result in the saddle point approximation and the result in the leading twist approximation, and then draw some brief conclusions. Okay, so as we know, the light cone gluon and quark distribution are defined as operator which sit on the light cone, and they are connected by gauge link. But unfortunately, as we know, this object cannot be calculated from first principle on the lattice. However, some time ago, G proposed a way to consider this object on the lattice by considering the same object but separated by a space-like separation and connected by a Wilson line, and by considering an infinite momentum frame, then this object slowly go on the light cone, and correction are given as inverse power of this infinite momentum. Since then, many people have worked on this subject. Here, there is just a very short list of all the people that have worked. There are also other kinds of the definition, like the pseudo distribution. But for what we need is definition are enough. And how do we, what we would like to do, as I mentioned in the outline, is to calculate the low X behavior of this object. And we will do this by taking the saddle point approximation and also taking the leading twist approximation. Okay, so how we actually do this? First of all, there was an observation made in the paper by Balisky, Morris, and Radusky, where they have considered the general Gluon matrix element and considered the tensor decomposition of this object, and given this as a linear combination of this tensor structure. These tensor structure are given as are made by the momentum of the proton p mu, the position x mu, and the symmetric tensor g mu, and multiplied by these amplitudes, which depends on this invariant x square and x dot p. So our goal is to obtain a result which is which depends on this invariance. The light cone distribution are actually related to only one of these amplitude, namely the MPP, and these are and the PDF are determined by this this amplitude. Unfortunately, this amplitude is not easy to isolate, but life for once it becomes easier at high energy, because there is this relation which tell us that the amplitude MPP, which is, as I said, determines the PDF, is given as a sum of the transverse component of this Gluon matrix element and the zero transverse component. Now, at high energy, we know that the transverse components are suppressed, and that we don't distinguish between the zero component and the three component. So just a quick reminder, here we are considered the third component. Therefore, in the high energy limit, we can analyze this quasi-PDF by considering simply the object M plus perp, M plus perp. Okay, so now let us remind what is meant by considering the leading residue and how it is related to the leading twist. So if we consider twist 2 gluon operator, we know that the anomalous dimensions are singular at j equal to 1. And we also know that the analytic continuation of the anomalous dimension at this point are determined by BFKL equation. Indeed, if we take this j equal to 1, is equivalent to take Bjorken x equal to 0. One just needs to remember the Diglap splitting function in Mellin space and in x Bjorken, and you see that when x Bjorken goes to 0, you have divergence as a 1 over the Mellin parameter minus 1. So we see that when j goes to 1 and coupling constant is very small, there is a new hierarchy of perturbation theory, which means that there are logarithms to be resummed, and we all know these logarithms are BFKL. Okay, so this j equal to 1 is usually called a physical point because it is when j goes to 1, this operator becomes non-local. The problem is what is exactly this non-local operator. Suppose we take a different scattering cross-section. We know that it can be given as a convolution of the impact factor of Pomeroy residue, also called, with the resummation of the logarithm, which are given by the exponentiation of the Pomeroy intercept, which is here this aleph nu. And if we take the nth moment of this structure function, then this moment of structure function with this with the cross-section given by this resummation, it becomes an integral over the parameter gamma, which is an integration which runs from minus infinity to plus infinity along the imaginary axis. So if we want to calculate the leading contribution of this object, it is equivalent to take the leading residue, because the leading residue is the one which does not vanish as q squared go to infinity. So we are in the ADS limit, which means q squared much greater than p squared. Therefore, the leading residue will coincide with the leading twist contribution. Okay, so if we want to calculate the leading twist contribution to our object, then we just need to repeat these steps. But actually, to do this, we really need an explicit expression of the operator at this unphysical point. And it turns out that this operator, this physical point, are light rate operator with point splitting, as it was observed by in this paper. So what actually was observed in this paper is that once you take this analytic continuation of this local operator, they are singular in the BFQL approximation, but you can regularize this object by considering this splitting in the transverse space and obtain this Wilson frame. So this Wilson frame, it should remind you as a dipole. If instead of this frame you take a dipole on the IS, this transverse distance is this transverse distance of the dipole. However, instead of this Wilson frame, one may consider also a different splitting point, which is exactly a straight line, and it coincides exactly with the quasi-PDF frame. So we will consider this operator with this gauge link and obtain this and analyze these operators to obtain the leading twist contribution. But how we do this? So first of all, how are these point splitting defined? They are defined in this way. We have simply the bilocal operator at point x perp and point y perp, but they are linked simply by gauge link without any frame. So this is just a simple straight line. Similarly for the Quark operator. Okay, so these are the objects that we have to consider. Now we have constructed the operator. How do we analyze this operator at small x? And we will do this by the OPE formalism. So as we know, if we consider deepness scattering cross-section at high energy, we know that this object can be studied within the OPE by splitting all the fields in classical and quantum and study the propagation of this quark anti-quark pair in the background of the classical field, which we know it reduced to a shock wave. The integration over the fields, the quantum fields reduced to a coefficient, and it is convoluted with the relevant operator, which are infinite Wilson line. So this expansion is written down here. At leading order, we have also contribution for the next leading order. But what we really want is the leading log approximation. We are looking for this kind of expression. So the idea is that once you know the impact factor, you calculate the evolution of the matrix element, solve the evolution of the matrix element, which is, we know, BK or Jim work, but we are interested in the linear evolution equation, therefore we will limit ourselves to BFKL, solve it with the model and convolute with your impact factor. So that's what we have to do. But the difference is that our left-hand side is a different object. This left-hand side are exactly our quasi-PDF. So to calculate the evolution of this object, to calculate the behavior of this object to small x, it's equivalent to calculate the structure function at small x. So we take this object, apply the OP formalism, obtain an expression which is equivalent to a coefficient function or impact factor, and convolute with the relevant matrix element, which are again these two Wilson lines, and similarly for the Quark. The diagram relevant for the diagram which give us these two coefficients, those two impact factors are exactly these two diagrams. And notice that here zeta2 will be the position of the gluon crossing the shock wave in this OP formalism, and zeta1 will be the point of crossing the gauge link. So this point, just a technical comment, this point is not actually fixed, but it has to be integrated between x and y. So, okay, once we calculate this diagram, we have to convolute this object with the evolution of this matrix element. And this will be BFKL, written in terms of Wilson line. BFKL is this nice looking compact form, and the solution is given here. Another feature of this procedure is that we are working in a coordinate spaces. Therefore, we have to translate everything in a coordinate space. This parameter A is exactly the parameter which resumes the important logarithm, and we have the exponentiation here of the Pomeroy intercept. This initial condition will be given by a GBW model or alternatively by the Mehtar-Goblar model. And as usual, QS is the saturation scale. Okay, so
Giovanni, you have 3 minutes.
Okay, so I'll be quicker. What do we mean by considering this object at high energy in coordinate space? Well, we know that when we consider small x, we mean that we fix the resolution of the virtual photon and send the center of mass energy to infinity so that x Bjorken is small. This is translated in coordinate space in the following way. The transverse distance of this object, x and y, is kept fixed, while the longitudinal coordinates are taken very large. And the parameter which resumes the important logarithm is this parameter A. And this is done in this paper. Therefore, we will use that result. And if we calculate those diagrams, we convolute the impact factor with the solution of the evolution equation with the GBW initial condition, then this is the result that one gets. The result is that the Quark and Gluon quasi-PDF grow with this x dot p, which is Joffe time, exponentiated by this Pomeroy intercept. This was for the saddle point approximation. What about the leading residue or leading twist approximation? First of all, in order to understand that we are on the right track, that our calculation is correct, always or usually one refers to conformal field theory and check whether the calculation is going in the right direction. So if we consider a two-point function in a conformal field theory with two supersymmetric light rate operator Sj prime, this conformal field theory tells us the general expression that these 2 points should take. So in practice, what one should do is to take this gluon correlation function and consider this in the high energy limit and check whether this correlation function reproduce the expected result from the general conformal field theory by explicitly calculating this structure function in this particular limit. And this is what was done with the Wilson frame, but it is also done, it coincides also with the quasi-PDF frame, and it reproduces the result of the 2-point correlation in the conformal field theory. This is done for the Gluon operator and for the Quark operator. So once you are sure that you are considering the correct residue, you can repeat this for the problem at hand. I remind that what we need to do is not to take this correlation function, but is to take basically half of it. That would give us the leading twist contribution for our quasi-PDF. But I repeat, taking this correlation will tell us whether the result is correct because it matches with the conformal field theory, and therefore we know that we are taking the right residue and the calculation is correct. Okay, what we really need to do very quickly is to take the local operator and construct the supermultiplet. These supermultiplet are multiplically renormalizable if they are written in this linear combination. Out of this local operator, one can construct the analytic continuation. And once you have constructed this analytic continuation, you may obtain the multiplically renormalizable operator with now analytic continued to this non-integer j. And now that you have this object, you can consider the correlation function. Okay, besides this technical consideration, I show you here the result. If we consider the leading twist contribution for the Gluon and Quark distribution, we get this expression. And notice that here we have two different behavior according to two different range of the product QS times this distance. I remind you that this X is exactly the point where one of the field is sitting. So if we take QS between 0 and 1, we get the usual modified Bessel function. On the other hand, instead, if we take QS times X greater than 1, we get a Bessel function, which has an oscillating behavior. Okay, so conclusion, I have shown you how to get the small x behavior of the quasi-PDF in two different ways by application of the operator product expansion. If we consider the saddle point approximation, which capture the full BFKL dynamics, then we get an exponentiation of the Joffe time and the usual growth of the distribution. Then we used the correlation function in conformal field theory to understand which precise residue, leading residue we have to take, because we reproduce the conformal field theory result. And then we apply this to the specific case of the quasi-PDF Quark and Gluon, and obtain the two different behavior according to the two different range of QS times X that may be considered. Okay, thank you.
Thank you, Giovanni. There's a question from Yacine. Yacine, please make it short because, okay, we still have your talk to go.
Oh, ahead. Yeah, so I'll make it short, sure. So can you go to slide 11? Just maybe concerning the systematics, just maybe naive question. Is this 11 maybe before that?
No, it's 13.
Yeah, that one. Now that the next one.
This is 11.
Yeah, next one then, and then the other one, the one that we exactly this one. So you have this shock wave in the middle, you know. So you're using this high energy approach. But how? So when I look at the left-hand side of the equation, when you see, look at the definition of the Gluon distribution, how do you motivate your insertion of the shock wave there? Is it taking x plus to infinity, or so? What's the logic? But there's no a priori no scale there to justify a separation of scales, right? Or is there one? So the point is that the gauge link that connects 0 and x is filling all of the space between the 2 points.
Yes, but indeed, as I mentioned, one is to consider this as and parameterize as a straight line between these 2 points, x and y, and integrate over this range between x and y. So z1 is not a fixed point, but it is, you have to integrate over the full range.
Okay, but there's an idea that the gauge link there is somehow confined to a shorter longitudinal extent than x minus y, right? Or not?
So what you do is the following. You take this gauge link and split this gauge link in quantum and classical. Then you realize that your gauge link is living only within this infinitesimal gauge link between, call it x plus and y plus. But once you do that, you have this gauge link at point zeta1. This gauge link actually can be extended to plus and minus infinity, which gives you this uz1, because the classical field is living only within this tiny shock wave support, and outside the shock wave, the field strength is 0. A pure gauge can be chosen to be 0, and therefore this infinitesimal gauge link can actually become an infinite gauge link. But the point in z pair, the point z1, z pair, has to be integrated between the full range.
I see. So I can see why this would work for the Gluon operator, because you generate large log 1 over x, right? But for the Quark operator, the Quark operator, yeah, I don't see why this would work here, because there's no phase space enhancement for Quark PDF.
Sorry.
There's no log 1 over x associated with the Quark PDF.
Why? What do you mean? There is. It's suppressed by 1 over n by 1 over energy, but
okay. So if you go to the higher power energy, yes, okay.
Yes, of course, this will be suppressed in comparison to this, but you can still resum logs.
We have another question from Ian, but please make it short because there is another talk.
No, not actually a question. I just want to answer to Yacine that what remembers in this formula about shock wave is the big momentum p. That's it. X, of course, knows nothing about shock wave, but the proton does. So that's it. And the approximation is valid at large peak going to infinity.
Okay. All right. Thanks.
All right. Thank you very much, Giovanni.
Okay. Thank you.
We will continue with our last speaker of the session, Yacine Mehtar-Tani. Yacine, could you please share your slides? Can you make it full screen?
Sure. Okay. Do you see the cursor?
Yeah, we do. Okay, perfect.
Thank you.
Yeah, you have 15 minutes. I will warn you after 12 minutes.
Okay, thanks. Yeah, so my talk is somewhat related to the two previous talks, Giovanni's and Jamal's. So the goal in this work was to try to connect the Bjorken limit and Regge limit. And so we started looking at the first example that we might tackle is inclusive DIS. And the byproduct of such an approach, so the idea was really to develop a systematic approach beyond high energy limit to connect the two, the Bjorken limit and the Regge limit. So the byproduct is a new unintegrated gluon distributions that is simple enough to kind of draw some attention. So okay, so this work was done in collaboration with Renaud Boussari while he was at BNL. So we have already two papers on that. So let me just say a few words about things that have been already discussed many times and introduced throughout the day. So we have two pictures, right, of basically hadronic collisions. So at high X, we describe the proton as just a freely interacting gas of partons, and but at low X, when X decreases, we have the rapid rise of the gluon distribution and gluon number. And in this regime, there's the breakdown of the partonic picture. So we'll have to resort to a different description, which is strong classical gauge fields. So this is somehow reminiscent of the wave-particle duality. So what happens in that regime, small x? So of course, at moderate x, increasing q squared for fixed x, moderate x, by increasing q squared, we are resumming logs of q squared via the DGLAP evolution equation. And this is, in effect, qualitatively, is increasing the resolution of our microscope here. In the other direction, the other hand, fixing q squared, which is basically fixing the size of our modes in the proton, by decreasing x, which is increasing log 1 over x, we increase the number of gluons, until, of course, we hit a certain boundary, which is the saturation scale, where nonlinear facts become important. So gluons start recombining. And this is exactly the regime of strong classical fields. And what we do here using the BFKL and the BK GMOC equations is to resum large logs of 1 over x. So, of course, the holy grail is to be able to connect the evolution, small x evolution, and the moderate x evolution by DGLAP. So this was tried in the past, and today what I would like to share with you is a new perspective, which is more akin to the approach of background field methods. All right. So what do we do at high energy scattering? So we apply this factorization, rapidity factorization. So at small x, the dominant diagram for DIS. So I have cut off here the electron part, the electronic part. So this is the virtual photon that's exchanged with, say, the proton. So high energy, we especially in the frame where the photon has no transverse momentum, you can look at it as this photon that moves at a very high velocity on the plus z direction that splits into QQ bar pair, which then interacts with the target by exchanging longitudinally polarized gluons. So that's basically the picture at high energy, and that's the Regge limit, where S here is related to basically the photon target system. So S goes to infinity, while the Q squared, which is related to the momentum exchange here, is small. So what do we do? So you've already seen this many times. So we apply this rapidity factorization, but that's just the first step of the approach, the so-called shockwave approach. So the first step is to separate what are quantum fluctuations, the blue fluctuations here, which are referred to as fast gluons. And then you have the slow gluons, which are treated as classical fields of the target. And of course, this is made possible because of the large phase space in the Q plus variable here. So you have a large rapidity interval here that allows to separate the two regimes. There's another approximation, which is related to the shockwave itself, right? So we, by assuming that, of course, the shockwave has support of the order of 1 over square root of s, then which technically would amount to simply boosting the target in the minus z direction, then we see that the target is dominated by this A minus component of the gauge field, and its support is of order 1 over p minus. And this is what we see here. So there's another large rapidity separation, which is now in the direction, Q minus direction. So we have a Q plus, strong Q plus separation. There's also strong Q minus separation, which is related now to the Yoffe time related to really the X variable here. So the size of the shock wave goes like 1 over P minus, 1 over square root of S, while the quantum fluctuation here is long-lived. That provides us another separation. So if you apply these two steps, the first step, which is the rapidity factorization, separation, and then the shockwave approximation, then you end up getting Wilson lines, this dipole operator that factors out of the hard matrix element nicely, and that's how you get the factorization at small x. And then you get Wilson lines here that extend in x plus from minus infinity to plus infinity. So that's the recipe. Now, you can compute the quantum evolution of this object that resums logs of Q plus. This was done in the 90s here by the famous BK equation in GMOC. More recently, the NLO equation was derived and put on a computer. And one of the observation was that at large rapidities, the equation was unstable. And this somehow triggered many studies trying to figure out what made this instability and how to fix it. All right, so very quickly, it was realized that this instability was due to collinear logarithms that double logs that simply are enhanced by the existence of small dipoles that radiate larger dipoles. That's how you generate. You might generate collinear logs, which are standard DGLAP logs. So if you at NLO, you could have an NLO relative. If you compare NLO to a leading order, you could have potentially large contribution, relative contribution, which is responsible for such instability. But this instability is again related to the fact that there is that the evolution variable in BK is independent of X-perp. And in some and one of the consequences of such an independence is that you might violate the K minus ordering by ignoring this correlation between these two variables. Now, if you restore the ordering, then of course, then you will account correctly for such double logarithms. So this was done in the past several years. So as I said, several solutions have been proposed. So by implementing a kinematic bound, modifying the evolution kernel, or changing the evolution variable. So all of these fixes are applied to the BK equation. So now we want to do better than that. So let's maybe list a number of limitations. So the first one is that it spoils the randomization picture that was established at leading order. We would like to have an order by order randomization picture. So there's a scheme dependence to how you would fix, how you would treat those collinear logarithms. And there is no operator definition that would systematically account for this, these double logs. And lastly, this corrections were not discussed at the level of observables. So when you discuss factorization and evolution, they go hand in hand. So you need to go back to discussing the observable and the impact factor. And then from there, you want to be able to discuss any modification of the small x evolution. So what's the problem? Well, the problem is the x dependence. So there's an ambiguity in small x, as I mentioned before. And the choice of the factorization or the rapidity variable that you would choose to factorize the slow and the fast modes. So technically, at leading order, there is no x. So x equals to 0 in the Regge limit. And only when you implement quantum evolution would you see the x dependence showing up in your dipole operator. So now there is this ambiguity with the x dependence. And there is another problem that was in fact realized in the 2000s by Bialas et al., where they tried to impose an x dependence in KT factorization. And they realized that imposing an x dependence would generate non-locality and transverse space which is incompatible with a dipole model. That's another reason why trying to have an X dependence should be somehow discussed at really the observable level. Try probably to reconsider the shockwave approximation. So neglecting X in the distribution is the origin of this large collinear logs that somehow plague this NLO decay. So what can we do about it? Or what else can we do about it? So we would like to revisit the shockwave scheme and try to restore the X dependence of the gluon distribution. So that's our somehow plan. All right. So the origin of the breakdown of the K minus or the loss of K minus ordering is related to a loss of an X plus ordering or correlation of the integrations. So if you, in the shockwave approximation, there is a decoupling of the time, the splitting time of the photon from the gauge fields of the shockwave, so that you would integrate the splitting time from -infinity to 0 for the photon splitting, while for the gauge field in the shockwave you integrate from the entire space, which is -infinity to +infinity. So there's a decoupling, and the overlap region is assumed to be suppressed by powers of the energy, and that's the logic. But now we see that we need to be more careful about how we treat the boundary. So there's a boundary problem that is necessary to account for the correct collinear logs. Of course, at leading log, you wouldn't see the problem, but next to leading order in the high energy evolution, you start seeing collinear logs, and then you need to be careful with the boundary when x's are of the same, x plus are of the same order, or equivalently k minuses are of the same order. So the question is, what is then the extent of the shockwave that we have to redefine somehow? So,
you have 3 minutes.
3 minutes, okay. All right. So, so the solution is to pick the first interaction in the shockwave that defines the first boundary of the shockwave, and the last one that defines the other boundary of the shockwave. And you would have 4 diagrams, so two diagrams here for the hookings of the first interaction, and 2 diagrams times 2 related to the hookings in the final interaction. So you had 4 diagrams, but in fact they combine together using, for the simplest expression of such a combination, the 2 diagrams here, they combine to form the field strength tensor integrated over the transverse segment between the two, between the quark and the anti-quark. And in fact, they simply reflect somehow an underlying structure, gauge invariant structure that will show up later. So we end up having a new dipole operator, which is not yet fully factorized. But the point here is that the new factorization formula, not yet the final one, exhibits similarities with the shockwave factorization. So the wave functions are identical. The only difference is now we introduce here, we keep the phase that is explicitly dependent on the Bjorken X. And in addition, you see here how you generate a non-local dependence on transverse space. As you can see, you have the transverse size of the dipole before the scattering and after the scattering, which reflects the non-locality of the scattering in transverse space. All right, so we can simplify further. And so how to do that? So we want to drop all powers of 1/q² and 1/s that somehow are suppressed in either Regge limit and Bjorken limit. So we don't need the full expression, and we can do it systematically. So the way we would do it to kind of keep only the leading power 1/s and the leading power 1/q² is to resort to the classical expansion. So the propagator, the non-eikonal propagator inside the shockwave can be expanded for small transverse separations around some position, average position x. And what we get is Wilson line, so that's good news, times propagator, free propagator that accounts for the quantum diffusion, and that's very important. So in the eikonal limit, there is no such quantum diffusion. You get a delta function here, but in this approximation, you keep that phase here plus power suppressed terms that you can, of course, systematically include. But the point here is that keeping track of that phase plus the finite extent of the shock wave will allow us to connect directly with moderate X and have an explicit X dependence. All right, okay, so here's the result. So if you apply this classical approximation by keeping the leading power, you factorize now explicitly the X dependence from the KT dependence. So again, you would have in this new factorization formula the same photon wave functions as in the small x. The only difference is you have an additional delta function that correlates x, which is Feynman x, to Bjorken x, which is measured, to the kinematics of the loop here, the loop integral here. And that this variable is rather standard in when you perform a collinear expansion. And then you get this new unintegrated Gluon distribution, which is explicitly gauge invariant, which I will show in the next slide. And here it is. So this operator looks like a Wilson loop defined by finite longitudinal size, which is conjugate to the Feynman x, a finite transverse size, which is conjugate to KT. And of course, it's taken between two field strength tensors, which are living on this transverse segments here. So this object is fully gauge invariant. Now you can see very quickly that this object, by integrating over KT, you recover, so the transverse distance goes to 0, collapses to 0, and recover the standard Gluon PDF. And then when you take x to 0, meaning neglecting the phase here, the x phase, you get the small x dipole operator as it should. So this somehow, this operator definition connects these two limits nicely. So this brings me to my summary. So this work was motivated by this discussion about collinear logs at small x, and we wanted to develop a systematic approach that would account for such collinear logs at the observable level, and being able also to compute corrections to that systematically. So the good news is that we have a minimal correction of the semi-classical approach of small x that solves this problem by providing natural dynamical account for for the k- ordering, and that the byproduct is that we have derived a new gauge invariant unintegrated Gluon distribution that's compatible with the x dependence in moderate x, and of course with the small x definition of the hadronic operator. So the outlook is, of course, to compute quantum evolution for this Gluon distribution, investigate other processes, which we are in fact currently doing, like DVCS and so on, and probably even tackle the problem of universality of such a distribution. And then last but not least, which I think is an important prospect, is to investigate, use this distribution on the lattice using those techniques, Euclidean QCD, to be able to probably investigate Gluon saturation on lattice and maybe measure saturation scale by varying now the X dependence of your operator here. And thank you.
Well, thank you, Yacine. It was a very nice talk. We have a question from Jan.
Hi. I have a question. Of course, on lattice, you can calculate whatever operator you want. But this particular operator, which you suggest, how it comes as a result of factorization? For example, when we factorize so Drell-Yan process of Higgs production in rapidity, we get exactly Weizsäcker-Williams type of the operator. F mu gauge link to minus infinity, gauge link from infinity to F mu in another place, and that's it. So from what factorization do you get your operator, or is just a convenient construct to study on lattice or something like that?
So, okay, so there are two questions here, right? So related to lattice and factorization. So
no, lattice no question. Lattice no question. Question is the following. I take Higgs production, for example, Odderon. How I factorize to get exactly your operator?
Well, we haven't considered other processes other than the EIS, inclusive DIS. So here, the point is that there is a difference with TMDs. So you mentioned past pointing or future pointing Wilson lines. In this case here, you have finite length Wilson lines. So this because the observable is inclusive, right? So I don't think we should look at this factorization as a recipe for application to other processes. We don't know yet how that might work, but rather as an extension of high energy factorization to the problem of DIS, right? And
okay, fine. So basically you say that in, say, Higgs production, you don't think the operator will be like you presented, yes?
No, I'm not sure about that, yes. No, I'm not sure.
No, okay, thank you.
But for say for processes that really are related to DIS, say for instance DVCS, then we know this operator appears, right? So this is something that we already observed.
Okay.
Okay, we have another question from Farid.
Hi, Yacine. Just a naive question. So this new Gluon distribution that you define, it looks like Weizsäcker-Williams type. So I was curious. You say that when you take the limit x going to 0, you get the dipole. But that's a bit counterintuitive to me because usually I thought of I think of the Weizsäcker-Williams coming from quadrupole.
Right. So the Weizsäcker-Williams, yeah, it's not a dipole distribution, and so the Weizsäcker-Williams, you have two field strength tensors that are connected to future pointing Wilson lines at two different transverse positions, but the Wilson lines, they go all the way to infinity and they connect at infinity, right? That's how they connect. Now in this operator, the two field strength tensors, the Wilson lines leave in between, right? They don't extend to infinity as you can see here. So they leave between the two field strength tensors that I can find. And that's the difference with the Weizsäcker.
Oh, I see. Okay, yes. And now I understand the difference.
Right. And if you want to reproduce the dipole, you simply somehow integrate over by forgetting about the phase, then this field strength tensor just becomes a derivative with respect to x plus, and then integrating, you get a total derivatives, and then that's how you recover UU dagger out of this. So UU dagger already here, sitting here. So these are the two lines here. Just the field strength tensor were recombined to give you what you need to reproduce the UU dagger.
Thanks.
Right. There is a question from Renaud, or maybe a comment. I don't know. Renaud, go ahead.
Yes, this is actually an answer to Jan Balitsky's question. I'm very confident that if you were studying forward Jalilian, inclusive Jalilian in the hybrid framework, then you would find the same distribution because it's also an inclusive process with the dipole type distribution at small x.
All right. Well, Jan, if you
can I have a question?
Yeah, that's not what we got with Andrei. Please find the mistake in our factorization then.
Right, you have to rely on the hybrid ansatz. So you'd have a quark with zero KT, and then if you factorize the rest of the amplitude with this scheme, you would find this distribution as well. But you have to
then they should be equivalent.
Yes.
Okay, I haven't thought about the equivalence.
I think this
Wilson lines go here between 2 points, not to infinity and back. And
yes.
If you consider Jalilian, they go to infinity and return back. It's unavoidable. It's because of the physics of the process.
That's why it has to be hybrid, because then you would integrate over the incoming quark transverse momenta, which would close them at infinity into just a straight line, which is finite after that.
Integrate over, can you repeat, integrate over what?
If you're, I'm talking about inclusive Jalilian, fully inclusive Jalilian, right? So in that case, you're integrating at the quarks.
Yes. That may be. We haven't thought
about I mean, it's important to distinguish inclusive, fully inclusive from, say, less inclusive. like CDs and Drelian, where you measure transverse momentum, where you basically in the realm of TMDs. This is not a TMD.
Since we are talking, your operator arises as a result of what? Factorization in deep inelastic scattering. I take amplitude of deep inelastic, I factorize in what parameter?
So there is a factorization in rapidity K plus, in the variable K plus, right? That's the first point. And
then
second,
you need to compare with our paper with Andre when we were talking about deep inelastic scattering in terms of rapidity evolution.
Right. Yes. This is the same problem, right? Now you have another variable, which is K minus, right? How do you treat them consistently, right? That's the question. Then you can either introduce a cutoff, and I think that's what you do with Andre, right? Introduce an additional cutoff to separate what's inside the shockwave and what's outside, right? What we do here, instead of introducing a cutoff, we dynamically somehow separate what is somehow outside the shockwave and what's inside the shockwave. And what defines the extent of the shockwave is no longer a cutoff that would sit outside the shockwave, but rather this field strength tensor itself that defines the extent of the longitudinal extent of the shockwave. So the question is, of course, whether they're equivalent.
Yes, and whether it's a proper way, because normally we have either apparent expansion or effective action with the clear definitions of the cutoffs. Yes, and this are kind of phenomenological estimate. Maybe
no, I wouldn't say phenomenological estimate. This is until this point. If I go back here, until this point, this formula is general. I didn't. So it's rather general when I expand in on the light code.
This operator has some cutoffs. Dipole is not given. Yes, it
should
be defined.
Yes, it's a cutoff in K plus. So it's here it is. So I'm using
K plus. Okay, we are too technical probably for the people. Let's.
Yes. So there is a cutoff in K plus.
Yeah, that's agree.
Okay. So we start with this, but then when we come here, right, which is the shockwave, the step 2 shockwave approximation, where we assume that the longitude, the quantum, the lifetime of the quantum fluctuation is much larger than the shockwave, and that's the second approximation in shockwave, by saying that the shockwave has 0 support.
Right? Yeah, I totally agree with Andre. We did the same thing. We assume that shockwave has finite length. It's what important.
Exactly. So we say it has finite length, but the point is, and here's the slide that's important, this is the approximation. If it all somehow boils down to this point here, what we do, instead of taking P plus to infinity so that we get this shockwave approximation for the propagator, what we say, we take it the other way around. We don't take Q plus P plus to infinity. We say, well, let's expand around X, around the delta function X close to Y, because this is a distribution, right? Which is which might have some, rather a tricky expansion. So what we do, we expand around X going to Y. And the price you pay in this expansion is the same Wilson line, but now you keep the phase because now you have a correlation between transverse coordinates and longitudinal. So of course, if you take Q plus, if you don't care about the transverse coordinate, or here it's transverse momentum, then you take Q plus to infinity, and that's how you get the eikonal approximation, a shockwave. But here what we say is that we have to be careful, because even if X is close to Y, you can still have L perp large. And if L perp is large, then you might generate large logarithms. So somehow this is some new cutoff, so to speak, which might be related to your rapidity cutoff in some way.
All right.
Okay, thank you.
We cut the discussion here, and if you want to continue, you can take it offline. First of all, thank you very much, Yacine. It was a very nice talk. I also would like to thank all the speakers and the audience of this session. It was a very nice session. I really enjoyed it. Thank you very much, and see you in the next session tomorrow.
Thank you.